Hello, this is AP Computer Science with John Maxwell. Today we'll be going over a few things. The topics include matrices, 2D arrays, overloading methods, and recursion. And how does that fit all in the same boat? It really doesn't. It's just what is facing our students this week. So we'll start off with 2D arrays or matrices. Fortunately, looking at this file, all of you have some experience with arrays, and you know arrays are homogeneous data collections. Homogeneous because they are only able to contain one type. On line 4, you see that I've created a 2D array called MATI for matrix. When I say 2D array and matrix, I'm using the terms sort of interchangeably, but it only holds ints, and you can see on line 4 I'm using an initializer list to create each row 2, 3, 4, 4, 3, 2, 3, 2, 4, and that's what a matrix is. Okay, so you can also on line 5 read through the comments that you can create an uninitialized matrix. I'd call it Maddie again. And this is 3 by 3. 3 rows is the first coordinate, and 3 columns, which is exactly what the declaration in line 4 sets up. So basically, you have an empty 2D array if you create it like on line 5 with zeros in each spot. Here's a key takeaway: every row in the matrix is a 1D array. So each row is an array in itself. On line 8, I do the same thing, only I created of the double type. And we're going to get to business about, summing up the elements. But before we do, I'm just going to explain the row and column coordinate system for you again. And down here, I've gone ahead and created that array. Here's row 1, 0, column 0, and the value in that is 2. So row 1, column 1, the value is 3. Row 0, column 2, the value is 4. So 3 by 3, again, it's a zero-based system. Indices are between 0 and 2 if it's a 3 by 3 2D array. And you can follow through and see row 1 is having at the 0 column 4, and at the 1 column 3, and at the 2 column it has 2. So I've used the same values. You can look at it, but the key is to understanding the first element here is the row coordinate, and this is the column coordinate. So here is the concept of overloading. And on line 12 and 11, we have two methods of the same name: sum. So what are we to do if we're a poor compiler? How do we know which method to use? Well, it depends on the parameter here. The parameter here is an int array. Matty can properly be sent to this method, where the parameter here is a double array. And Matty D, which has been declared as a double array, can be safely sent to this. And that is the secret to overloading methods. Looking at the rules for overloading methods down here, we find that the method has the same name, in this case sum, and that there are different type, number, or order of parameters. Okay, so that's the way they differentiate. When you're trying to write code, it may try to correct you at the time, but like that notice compile time is static binding. The compiler looks for an appropriate method signature using the name and the parameter types. They do not overload based on differing return types, in this case an int, and then the other case a double. It is only the name and the parameter type, number, or order that differentiates the uh, calls to the two methods. And that happens at compile time, which is also something called static binding. And we'll talk about more about static binding when we introduce the concept of dynamic binding later on in the coming semester. So let me run this and show you that it produces 27 and 27.0. Wow, what did I type? Line 3. Oh, I look. I left a little apostrophe up here. Sorry. Let me just run it again. Okay, 27 and 27.0 because they have the same numbers. I did that on purpose. Let's get into what the sum method does. Okay, and this is the key takeaway, and it's something that you'll have to understand because there's always a part 2D array question on the AP CSA exam. Um, the process for iterating or traversing a matrix is the nested for loop most commonly. So you're going to, with the nested for loop, understand that for each step in the outer loop, here we go on line 14, the inner loop on line 15 executes completely. So when row is 0, column will move from 0 all the way to the end of the row. And it's called row wise or row major traversal. Okay, so what happens is it becomes row 0, column 0, add that to the sum. Row 0, column 1, add that to the sum. Row 0, column 2, add that to the sum. And then the inner loop is completed and it goes back up to the outer loop and it will process row 1, 1, 0, 1, 1, 1, 2. Okay, and it will do that until the entire matrix is processed. M dot length in this case returns the number of rows in the matrix. And since each row in the matrix is a 1D array, you can access the number of columns by accessing the length of that 1D array. So M square brace 0, the first row, dot length, and that will return 3. And so we move from 0 to 2. And please note, again, the most important concept or hidden concept that they test a lot on is that each row in a matrix is an array. So here we have an alt form using the for each loop. We take from M, which is the parameter given, and we take each row, int square brace x. That's each row. We're traversing and dumping the row into x. And then we go and dump the values in that row into y and add them to the sum. And so if you study that, that is a pretty quick and easier way to do things like summing and other elements. But if you need the access to the indices, you're going to have to use the traditional approach over here. Now, the sum of the double is pretty much like the sum of the int, but over here I want to tell you about column traversal. So traversal is to go through something completely. Here we have like explained to you a row major. This is a column major traversal. So you just switch the for loops. On the outer loop goes the column, so you're going to process each column. First the 0 column, then the 1 column, then the 2 column. And then you're going to grab the value for each row in that column. So you just basically switch the for loops to do a column traversal. So if you do a column traversal, you can't use that type of thing because each column in the matrix is not an array. Okay, so you can't do that for each loop thing with the column traversal. So the summary of what you've learned is a brief review of a 2D array or a matrix. You've seen a couple forms of how to declare it. And you've seen an example of an overloaded method, which is one that shares the same name but different order, types, or number of parameters. Again, not differentiating based on return type. And then finally, we looked at the use of nested loops to traverse arrays, both in a row and a column major way. And we also examined the use of a for each loop to do a row major type traversal. And this is all we want to know and talk about matrices today. Remember, there's always going to be a part 2 question on it. Students find and generally report that it is one of the harder of the part 2 questions. Because why? Okay, great. We're going to shift over to recursion. So I'm going to switch to a different file. And this is kind of ridiculous, but like, let me just put the number 10 here. Okay. All right. Base definition is that recursion is a method that calls itself. So I have a repeat method that takes in a single int parameter, and well, if n equal 1, return 1. That would be great if I sent 1 and it just return 1. Else, it's going to return, oh, wow, here's a call to its own method. It's a call to itself, right? So we got to think about that for a second and say, the first type of question, which is a multiple choice question that you might encounter on the test, is this infinite recursion? At some point it needs to stop, and that's called the terminating or base case. When n equals 1, it returns 1. That stops the recursion. Is it going towards that? N minus 1? I don't know. It will work for a positive number. So you really got to ask. They may ask what type of input would cause infinite recursion, and they'll have a bunch of values. So you want to see that the recursive call approaches the base case, which is the termination of the recursive calls. Okay, so let me run this, okay, and notice that in all cases it returns n. Okay, so let's look. What's going on here? Here we go. All right, so let's run. The first thing out is pass 1. Does that make sense? Well, let's look at it. It should make sense. Here we have, when it gets to 1, it returns 1, and then pass 1. Yeah, well, that makes sense. All right, and then pass 2, 3, 4, 5, 6. There seem to be duplicate values. Let me run it again. That happened last night. Okay. No more duplicate values. Don't know why that is. Pass 1, pass 2, pass 3. So certainly we know that like it works and calls recursively until n equal 1, and then it returns 1, so pass 1 gets outputted first. When the last call to the recursive method happens, the last one reaching the base case, then it allows all the other calls to complete their work. Okay, and the book has a pretty good picture of it, but I'm going to switch over to the call stack. And what happens with a call stack is that the compiler sets up a special memory space for that particular call. The variables aren't shared between different calls, okay? They are set up individually. And we'll return to that idea that recursion is sometimes expensive, okay, in that it uses a bunch of memory, or can. Okay, so the first call is 10, the original call, 10. 10 minus 1 is 9. The value returned is 9. 9 minus 1 is 8. The value returned is 8. 8 minus 1, 7, and so on until you get to the base case, 2 minus 1. So the value returned is 1. And then 3 minus 1, the value returned is 2. Okay? Because reaching the base case allows all the other methods to unlock and complete their work. What this is a last in, the call recursion 2, 2 minus 1. The last one in is the first one out, LIFO. And the call stack will collapse at that point when the base case is reached. The reason why I show you this table is when you're tracing recursion on the exam, you might want to set up a table that's appropriate for your problem. Counting in and pointing to the stack. So it will help you trace the code. Well, anyways, back to the code, okay? Now we see how this is done. Main 10, 10, what's returned here? 10. Okay. Now, recursion isn't just always useless, right? You know, this is useless, right? Outputting pass 1, 2, 3, etc. It performs no work except for the idea that like it shows you how recursion works approaching the base case. Here's an example of multiplication. Now I'm going to comment this out, show you how recursion can use multiplication. Okay. Well, on line 5 we're giving 3 and 7, and what is 7 times 3? 21, and that's the answer that's outputted. Well, it's kind of interesting to see what that looks like and how it works. And so you saw me quickly comment this out. I like to inspect the variables I and j here to just see what we're doing. And by the way, the base case is I equal 1, return j. All right, so it's j plus multi I minus 1 j. So I is 7, it's going to go 7, 6, 5, 4, 3, 2, 1. There you go. You hit the base case. So if I starts out at 7, yeah, it does approach the terminating condition, I equal 1. And what is j? J never changes, it's 3. So are we counting 7 threes? I think we might be, because that's the plus sign there. Okay, let's look. I mean, this is what's showing here. The first call is 7-3, right? It's out. That I'm sorry. Yeah, 7-3. And it's 6-3 and 5-3 and 4-3 and 3-3 and 2-3, and I can't show you 1-3, okay? Because the system out needs to be before the return statement. I can't put a statement after the return statement. It's an unreachable piece of code after the return statement. So count them up. We got one, two, three, four, five, six. Okay. The seventh three is occurring after here, after the last printout right here. Okay. So we're just adding up all the threes 7 times. We show six, but again, if I take this out and put it after the return statement, it wouldn't work. So there's one more three to go. And there's an example of multiplication, but like if I go 1,000 or 10,000, well, let's see what happens. Okay, perfect. I love it. I've overflowed, the memory in the computer. Let's look at when I did that. It started okay, I suspect. Okay, really doesn't allow me to go too far. Anyways, the problem with recursion is it can be expensive. Okay, each time a method gets set up, separate variables are set up. Okay, and they all occupy space, and it becomes difficult. So what we want to do is, recognize that. That said, okay, the recursion can lead to some elegant solutions. All right, particularly in the area of sorting. We're going to learn second semester that sorting, recursive methods in sorting are far better than other methods. So it's used in a variety of situations. Interesting enough, I heard it was used in guiding robots in search and destroy bomb robots, fire robots. Can't go into a burning warehouse, but a robot may be able to. So these are maze type problems where if you hit a dead end, you turn back to where you were before and try another direction. Okay, so recursion has some elegant type of solutions. Here's another one that I'll show you just before. It comes up with the power. Of course, 2 times 3 is 2 to the power of 3 is 8. Okay, and the base case here is y equals 0. It returns 1. Otherwise, it's x times the power of y minus 1. So we're going to go and decrease y to 3 minus 1, 2, 2 minus 1, 1, 1 minus 1, 0, return 1. Okay, so that's the way it flows. And let's run it and see that it can, again, calculate out 8. And it does it. So it every recursive method can be written using a loop. And that's why I never thought it was that important, except for some of the elegant solutions like searching and, I'm sorry, not searching, but sorting. But, you just have to say, as it was first presented to me, it's a matter of faith that the recursive calls are going to do their work. You design it and you hit run and you hope that like it will do its work, but you know about faith because most of you are, all of you are in a Catholic school, right? Who knew that like various incredible things that occurred actually occurred? You take it on faith. So recursion is like faith. And with that, I will just say thank you for watching. This is John Maxwell, and this has been AP Computer Science A.